If we are truly to prepare for the dangers of climate change and build more resilient environments, we must first understand natural climate change. Unfortunately, due to the narrow focus on rising CO2, the public remains ill-informed and fearful about the causes of retreating ice. Africa's Mount Kilimanjaro and America's Glacier National Park are two iconic examples of failed climate interpretations. For example, Al Gore's Inconvenient Truth suggested warmth from rising CO2 had been melting Kilimanjaro's glaciers. In truth, instrumental data revealed local temperatures have never risen above the freezing point. In 2004, Dr. Jeff Jenkins, head of the Climate Prediction Program at England's Hadley Center, was prompted by the evidence of no warming to email the IPCC's Phil Jones and ask, and I quote, "Would you agree that there is no convincing evidence of Kilimanjaro glacier melt being due to recent warming, let alone man-made warming?" Yet due to the politicization of climate science, Al Gore shared the Nobel Prize despite perpetuating the global warming myth of Kilimanjaro. Glacier experts from the University of Innsbruck published, and I quote, "The near extinction of the plateau ice in modern times is controlled by the absence of sustained regional wet periods, rather than changes in local air temperatures on the peak of Kilimanjaro. Changing patterns of precipitation were recorded in the water level of nearby Lake Naivasha. As the researchers documented in this graph, the region had experienced increasing precipitation during the Little Ice Age, followed by a sharp drying trend that began in the late 1700s, which triggered Kilimanjaro's retreat long before CO2 ever reached significant concentrations. Ice structures such as these penitentes are commonly seen in many high elevation glaciers and help scientists determine if retreating ice was caused by below freezing sublimation or melting from warmer air. Over decades, sublimation creates sharp features at the border between sunlight and shade. In contrast, any melting from warmer air temperatures oozes across the icy surface, destroying those sharp features in a matter of days. So the presence of sharp angled features like these penitentes are excellent long-term indicators of dry and below freezing temperatures. Over 30 years ago, I visited Glacier National Park, home of the second iconic example of misrepresented glacier retreat. After thousands of years with less ice, the park's glaciers grew to their maximum extent during the Little Ice Age. Then they began retreating around 1850. Although the media now hypes the park's disappearing glaciers as evidence of CO2 warming, the greatest retreats happened long before CO2 could exert any possible effect. In 1913, the park's largest glacier, the Sperry Glacier, was nearly 500 feet thick at a point that would soon become its 1946 terminal edge. By 1936, that thickness had dwindled by 80%. That rapid retreat prompted scientists 70 years ago to predict a natural disappearance of the park's glaciers. As seen here, the contrast between the early and late 20th century retreat is striking. Between 1913 and 1945, the rate of retreat for the Sperry Glacier was 10 times faster than the rate of retreat since 1979. If rising CO2 has been the driver of recent melting, then we should expect an increasingly faster rate of retreat, not slower. If we are to prepare for changes caused by melting ice, we must view our vanishing ice from a perspective of centuries and millennia. And that perspective insists that we understand natural climate change. There is an abundance of evidence demonstrating that relative to today, far less ice covered the globe during the last 10,000 years, a period known as the Holocene. Far less ice despite much lower CO2 concentrations. Likewise, although most of today's average global temperature has been driven by heat ventilating from the Arctic Ocean, as visualized in this NASA graphic, Arctic temperatures were also far warmer during most of the Holocene. Based on changes in tree line, pollen samples, and ocean sediments, Scientists estimate Arctic air temperatures during the mid-Holocene averaged 2 to 7 degrees centigrade higher than today. This ice core data from Greenland exemplifies the Holocene's changing temperature patterns common for most of the Arctic. But it is a pattern that also corresponds to climate change in many other regions across the globe. After the last ice age ended, the period of warmer temperatures between 9,000 and 4,000 years ago has been dubbed the Holocene optimum. During that time, remnant glaciers from the Ice Age retreated and shrank to sizes far smaller than we witness today. All of Norway's glaciers completely disappeared at least once. And Greenland's greatest glaciers, like the Jakobshavn, remained much further inland than now observed. Like many northern glaciers, Jakobshavn had only recently advanced past its present terminus during the unprecedented cold of the Little Ice Age. From whale bones, Arctic driftwood, and patterns of Arctic shoreline erosion, we also know that during the Holocene, Arctic summer sea ice retreated 1,000 kilometers further north than seen today. Tree lines advanced to their greatest northern limits, reaching Arctic shores 9,000 years ago, hundreds of kilometers further north than their current limits. The Paleo-Eskimos, or Tuniat, colonized the Arctic shoreline about 5,000 years ago. They hunted muskox and caribou with bow and arrow. They lived in tents and heated those tents with wood. Archaeologists studying Tuniat colonization of Arctic shores reported periodic abandonment and occupation that corresponded with periods when summer sea surface temperatures bounced between 2 and 4 degrees cooler and 6 degrees warmer than present. Likewise, concentrations of Arctic summer sea ice range from 2 months more sea ice to 4 months more open water. Changes in insolation due to the sun's orbital cycles, or Milankovitch cycles, correspond with recent 100,000-year cycles of past major ice ages. We are currently in another warm peak. The Milankovitch orbital cycles also predicted the current cooling trend that began about 4,000 years ago. However, warm spikes due to high solar output punctuated this cooling trend roughly every 1,000 years. The unprecedented Holocene glacier growth during the Little Ice Age occurred when solar output was extremely low. In this graph depicting 300 plus years of solar flux, the Earth warmed as we ascended from the Little Ice Age. Our recent warm spike coincides with high solar flux. However, recently, solar output has again retreated, approaching Little Ice Age levels, and correlates with the increasing frequency of cold winters. The next 2 decades will allow us to evaluate more accurately the effect of these solar changes on climate and glaciers. The correlation between Greenland ice core data and solar flux is seen in Scandinavian tree ring data. Tree rings suggest the warmest decade in the past 2,000 years happened during the warm spike of the Roman warm period between 27 and 56 AD. After a period of resumed cooling, a new warm spike occurred 1,000 years ago during the medieval warm period. After more extreme cooling during the Little Ice Age, a third warm spike peaked around the 1940s. Most interesting, the consensus from multiple tree ring datasets around the world also suggests natural habitats were warmer during the 1940s than they are now. Likewise, the greatest rates of retreat for glaciers from Glacier National Park to the European Alps also happened during the 1940s. The Great Aletsch, the largest and best studied of all Swiss Alps glaciers, beautifully illustrates the 3,000-year cooling trend punctuated with periodic warm spikes that cause rapid glacier retreats. The Great Aletsch's maximum length during the Holocene was also reached during the Little Ice Age. About 1850, it began retreating to its current position, represented by this baseline. However, during the warmth of the Bronze Age, 3,000 years ago, the glacier was much smaller than today. During the cooler Iron Age, the glacier began to grow, but rapidly retreated during the warm spike of the Roman warm period. The glacier advanced again, almost reaching its Little Ice Age maximum, but retreated rapidly during the warm spike during the medieval warm period. During the Little Ice Age, the Great Aletsch advanced to its greatest length of the Holocene, in rhythm with a series of 4 documented solar minimums. Each advance was followed by a rapid retreat, similar to what we observe today, when solar flux increased. The glacier's recent retreat does not appear any different from retreats in the past. So what does that tell us? To be clear, the skeptic argument is not, because it was natural before, then CO2 cannot possibly contribute today. The skeptic argument is simply, we cannot determine the sensitivity of our climate and glaciers to rising CO2 until we have fully accounted for the past and present natural dynamics. Far too often, the media and a few invested atmospheric scientists simply assert that retreating glaciers were all natural in the past, but since 1950, the retreat is suddenly due to CO2. But past natural climate dynamics did not suddenly stop operating in 1950. To what degree are natural climate dynamics contributing today? Well, more recent patterns of advancing and retreating ice suggest natural dynamics are the main drivers of today's retreating ice. The history of mass change measurements for several Swiss glaciers allow us to more finely resolve changes between decades. Again, the greatest rate of 20th century retreat occurred during the 1930s and 1940s, and once again before CO2 concentration had any significant impact. The rapid 1940s retreat is linked to unusually high solar insolation and patterns of precipitation governed by the Atlantic multidecadal and North Atlantic oscillations. Furthermore, when solar flux dipped between the 1960s and the 80s, a high proportion of alpine glaciers, as well as glaciers around the world, stopped retreating, and many began to advance, as seen here in the Alps. Changes in solar insolation affect oceans in 2 critical ways. During high solar output of the medieval warm period, tropical waters in both the Atlantic and Pacific increased by as much as 1 degree centigrade warmer than today. During the solar minimums of the Little Ice Age, tropical oceans dropped by as much as 1 degree centigrade cooler than today. But equally important, changes in insolation affect the volume of warm tropical waters that were transported towards the poles. Multiple lines of evidence correlate high solar activity during the Roman and medieval warm periods with an increased flow of warm Atlantic water into the Arctic, resulting in reduced sea ice. Conversely, during low solar activity, during the Little Ice Age, transport of warm water was reduced by 10%, and Arctic sea ice increased. Although it is not a situation I would ever hope for, if history repeats itself, the natural climate dynamics of the past suggest the current drop in the sun's output will produce a similar cooler climate, and it will likely be detected first as a slowdown in the poleward transport of ocean heat. Should we prepare for this possibility? Water heated in the tropics is saltier and denser, and when transported into the Arctic, lurks 100 to 900 meters below the surface. That warm subsurface water can melt sea ice and undermine grounding points of submerged glaciers, causing an acceleration of ice discharge. Intruding warm deep water also melts the underside of floating ice shelves, which also accelerates calving and ice discharge. Instrumental records of Greenland's air temperatures also recorded the fastest rate of warming during the 1930s and 40s, coinciding with increased inflows of warm Atlantic water. Accordingly, intruding warm waters also transported more southerly fish species, prompting the birth of Greenland's cod fishery. CO2-driven models have completely failed to simulate this Arctic warming. Simultaneously, the best-studied Greenland glacier, the Jakobshavn, began retreating from its Little Ice Age maximum with its fastest observed retreat of 500 meters per year between 1929 and 1942. The rapid retreat was amplified when the glacier's terminal front became ungrounded from the ridge. That earlier grounding point had previously prevented warm subsurface waters from entering its fjord. With more warm water entering the fjord, the grounding point rapidly retreated. When warm water intrusion subsided, the glacier stabilized and even began advancing between 1985 and 2002. Although the recent retreat of Greenland's glaciers is reported as an acceleration relative to the 70s, the rate of retreat is now much slower than the 30s and 40s. And again, the 20th century pattern of retreat does not correlate with rising CO2. The 20th century pattern of Greenland's melting glaciers correlates best with the timing and distribution of intruding warm Atlantic water. As seen in these illustrations, due to changes in the North Atlantic Oscillation in the 1990s, a sudden influx of warm Atlantic water entered the Erminger Current. The numbers here indicate that the current's temperature cooled from 10 degrees to 1.5 degrees above freezing as it traveled along Greenland's coast. As seen here from recent satellite estimates, the amount of Greenland's lost continental ice coincides with the warmth of the Erminger Current, with pinker areas representing the highest rates of lost ice. Warm Atlantic waters that don't enter the Erminger Current continue deeper into the Arctic, mostly via the Barents Sea. Greater volumes of intruding warm water cause greater reductions of ice in the Barents and Kara Seas, deep inside the Arctic Circle. Danish sea ice records reveal a similar loss of sea ice during the 1930s, rivaling the recent decline of sea ice in the Arctic today. Coinciding with cycles of reduced sea ice, glaciers on the island of Novaya Zemlya in the Barents Sea also underwent their greatest retreat around 1920 to 1940. After several decades of stability, its tidewater glaciers began retreating again around the year 2000, but at a rate 5 times slower than the 1930s. The recent cycle of intruding warm Atlantic water is now waning, and if solar flux remains low, we should expect Arctic sea ice in the Barents and Kara Seas to begin a recovery and Arctic glaciers to stabilize within the next 15 years. The contrasting behavior of Antarctica ice is further confirmation that intruding warm water is a natural driver of melting polar ice. Unlike ice that melted deep inside the Arctic Circle, Antarctic sea ice increased to record extents and expands far outside the Antarctica Circle. Why such polar opposites? Because the Antarctica is shielded from intruding warm waters by a circumpolar current. Antarctica's circumpolar current consists of warm subtropical waters driven eastward by westerly winds. Because there are no continents to block its path or deflect those warm waters poleward, the circumpolar current simply encircles the continent. The one place where Antarctica sea ice has retreated slightly only occurs along the western side of the Antarctic Peninsula, where the circumpolar current makes its closest approach. Likewise, without intruding warm waters, Antarctica has lost far less continental ice than Greenland. Although Antarctica contains 14 times more ice than Greenland, Greenland has lost between 2 and 5 times more ice than Antarctica. Based on changes in gravity, most areas of Antarctica have slightly gained ice, designated by greenish tones. However, where warm waters and winds of the circumpolar current approach the peninsula, there has been moderate ice loss, designated by bluish tones. And despite being Antarctica's most poleward coastline, there had been a great loss of glacier ice around the Amundsen Sea, illustrated by the redder tones, causing a net loss of ice for the continent. The reason for this concentrated melting is due to the upwelling of relatively warm circumpolar deep water that lurks 300 feet below the surface. Glaciers along the Amundsen Sea terminate in deep water and are most susceptible to periodic upwelling of that warmer, deep water, which causes basal melting. Maps pinpointing regions with the greatest basal melt highlighted here by the red dots, coincide with the greatest loss of glacier ice along the Amundsen Sea hotspot. Amundsen glaciers are grounded along the coastal shelf, where ancient channels can direct warm, upwell deep water directly to the base of the glaciers. Early explorers reported excessive crevices and concave surfaces on these glaciers, suggesting extreme basal melting was happening in the 1950s, and was likely a process that has been going on for millennia. Much like Greenland's Jakobshavn Glacier, once Amundsen Sea glaciers retreated from their highest ridge on the continental shelves, upwelled water could overflow the ridge and melt an increasingly larger cavity nearer the glacier's grounding points. In turn, a larger cavity allows even more water to enter. In contrast, the few Amundsen Sea glaciers with grounding points located beyond the reach of upwelled waters, those glaciers have not lost any ice. Like the rhythm of retreating and advancing glaciers, rates of sea level rise have ebbed and flowed as seen in the graph from the IPCC. Again, it is the 30s and 40s that experienced both the greatest retreat of glaciers and the fastest rise in global sea level. With the recent decline in solar flux and the shift to cool phases of ocean oscillations, natural climate change suggests that although glacier retreat and sea level rise will likely continue for the next few decades, the rates of sea level rise and glacier retreats will slow down. The next decade will provide the natural experiment to test the validity of competing hypotheses. Are changes in the Earth's ice driven by natural or by CO2-driven climate change? I'm betting on natural climate change. For a list of peer-reviewed citations used to support this presentation, please visit landscapesandcycles.net/shrinking ice. And read more about natural climate change in Landscapes and Cycles, an environmentalist's journey to climate skepticism. Thank you.